So I'm going to tell you about some efforts in solid state condensed matter physics to bring quantum gravity to the lab. And this is a work of large group of my students and postdocs, and I will also mention work by various other groups. So basically two things that I would like to address in this talk. Can one create black holes and wormholes in a lab using solid state platforms? And second, if so, what are the possible applications of these systems? Are they good for anything outside just demonstrating that we can do that? So black holes from interacting fermions, and for me, fermions will be electrons. In solids, we deal with electrons. So here, what we're looking at is ways to fabricate in the lab something that behaves as a Sachs-Devier-Kitaev model. And the first speaker today already gave you a very good introduction to the SYK model. So the only thing that I can add here is that I put in pictures of the protagonists, Subir Sachdev, Jean Vouillet, and Alexei Kitaev, who told us that if you take a system of n interacting either Majorana fermions or complex fermions with all-to-all random interactions, which can be depicted like this. This is dual to a near extremal black hole in 1+1 dimensional anti-de Sitter space. So can we somehow create a model that behaves according to that fermionic Hamiltonian in a lab? Just a very quick summary. SYK model exhibits extensive T equals 0 entropy. It has emergent conformal invariance at low energies. And also it thermalizes in shortest possible time that is consistent with causality and unitarity. And it is these properties that suggest strongly that it realizes holographically this black hole. And of course, we have more evidence from lots of papers out there that this is the case. The reason why we love this model is that, well, one reason is that it's soluble in large N. I'm writing a version of the model with 4 fermion interactions, which is what we want, which is what gives us all this wonderful physics. And I'm also writing these 2 fermion terms, which we don't want because they spoil all this nice physics. But in any realistic solid state system, they always want to be there. So I'm putting them in just so that we know what's there to come. Basically, for those who haven't seen this, one can solve this model using large N saddle point techniques. And it all boils down to just 2 coupled equations for the propagator and the self-energy. And the structure is not really important. I'm just trying to emphasize the simplicity of this all, which even a humble condensed matter theorist can actually put on a computer and solve in various limits and understand the behavior of this model and various variants that I will discuss. So, okay, again, as already Subir pointed out, most realizations that you would like to concoct in a lab have some sort of interaction piece, but they also come with this undesirable 2 fermion term. So much of the effort is then how do we get rid of those terms in the lab. And I jumped straight to proposed physical realizations. So there's few of them on the market these days. A very nice one was given by Jason's Alicia group at Caltech, who basically took the most developed a platform which has Majorana 0 modes, which is these semiconductor quantum wires, and proposed a scheme where you take n such wires, each having 1 Majorana at each end. And what they proposed is coupling weakly these Majoranas into a single disordered quantum dot. And I will not really discuss this in any great detail, but a beautiful and relatively simple calculation shows that under the right conditions at low energies, this realizes SYK model for Majorana fermions in the system. And of course, we have a world's foremost expert on quantum wires, Charlie Marcus, who will, according to his title, I think he will talk about this in his afternoon presentation, or at least he will mention this probably. So here's another proposal. This is another platform that hosts Majorana fermions in solid-state systems. This is the famous Foucault superconductor, where what you have is an interface between a topological insulator, and we have lots of those, and an ordinary superconductor. And what Fu and Kane showed is that at the interface, a special topological superconductor is generated, which has a property that if you apply magnetic field to it, then each Abrikosov vortex hosts a single unpaired Majorana fermion. So that's another platform. There is some experimental evidence that this actually occurs in certain systems. And so can we harness this to create a SYK model? The answer is possibly yes, although in this form, when Majorana fermions form a lattice, this is not the right geometry because they don't really interact strongly and they don't interact all-to-all. But what we could do, we can deform this. We can coax all these Majorana zero modes to be in one place by basically fabricating a hole in this superconductor and trapping n flux quanta in it. And this is work that we've done with Dima Pikulin some years ago. Dima is also here in the audience. And one can show that at low energy under the right conditions, the physics of this maps onto the SYK model. Now, let me take this opportunity to address this question of quadratic terms. I told you that most physical systems that you consider, the leading term in the Hamiltonian is usually this quadratic coupling that you don't want. So how do we get rid of it in this particular case? Well, so this quadratic piece or hybridization occurs simply because the wave functions of these Majorana fermions overlap between neighboring vortices, and this overlap to leading order just leads to this bilinear term. And it's always there unless you can prevent it. And the way this can be prevented in this situation is by exploiting a symmetry. This model happens to have what one may call fictitious time reversal symmetry at a special point in parameter space. For those of you who know about topological insulators, if you tune the chemical potential of the surface state down to the neutrality point, where it coincides with the Dirac point of the surface state, then the system is more symmetric and it has different topological classification, which basically means, bottom line, that this term is prohibited by that symmetry. So in principle, by tuning a single parameter, which can be tuned in the lab by gating, for instance, one could get to the point where these bilinear terms that are not good for SYK are all 0 or close to 0, and the next term in the expansion of the Hamiltonian is precisely the SYK, and this is what we showed with Dima a couple of years back. So we did lots of tests to show that this is indeed true. One can calculate various things like thermodynamic entropy. One can do level statistics analysis, and it all checks out for the reasonable number of fermions that we can simulate on a computer, up to, I think, 32 fermions. We see a good agreement between what is expected and what we calculate from this model system. Now, this is not a very easy proposal to realize, and we thought some more about, is there a simpler system out there that can realize this SYK physics? And here's a proposal that I think actually can be realized in the lab. It's based on a graphene flake, and I will go quickly because I have some other things that I like to talk about. So basically the result is the following. If you take a single graphene flake of a nanoscale size, hundreds of nanometers in size, which has a fairly irregular boundary, and you apply strong magnetic field in a plane perpendicular to it, then at low energies, the electrons are described by the complex fermion version of the SYK model with these bilinear terms, again, being small or negligible due to something called the chiral symmetry that is present. And it protects this zeroth Landau level in single particle excitations from broadening, which is the same as saying that those bilinear terms are absent or small. And this is a proposal that actually could be done in the lab. One could test these ideas by doing spectroscopy. Scanning tunneling microscopy, for instance, measures basically the spectral function of the electron, which should show, if it's described by SYK, this characteristic inverse square root dependence on frequency. That would be one signature. We worked out also signatures in charge transport. And again, I don't have time to go to details, but if anybody's interested, I can discuss that later. Basically, there's specific signatures in temperature, bias, and magnetic field dependence that this system would have in transport if it were described by the complex SYK model. So there's some candidates. The ball is in the court of experimentalists. How about wormholes? So can one make wormholes, as Juan was discussing? And indeed, one could. And this is, again, we're thinking about two coupled SYK models via these bilinear mutual couplings that put the system into something that is close to thermofield double state. Basically, all these proposed systems that I discussed that should realize SYK, if you double them and couple them, then they should realize a wormhole, at least on paper. So just a quick reminder of what Juan said in the morning. Basically, two identical SYK models coupled in this way produce this eternal traversable wormhole, and the ground state of that combined system is very close to this thermal field double state, which is fascinating for many other reasons, and I will touch upon that later in my talk. When I heard first about this, I was excited because I like wormholes, and I was a Star Trek fan, although I'm being told that these wormholes will not be good for interstellar travel, so that's a pity, but one has to start somewhere. So possible experimental realizations that we are starting to think about are basically doubling the proposed experimental realizations of a single black hole, so that if you have a single SYK, if you can make two of them and couple them, then that would basically realize this wormhole. There's problems with this or challenges that I will mention, but pretty much every such realization that I had previously, for instance, Jason Alicia's quantum wires, can be naturally complemented to realize something that looks like a wormhole. So for instance, I added here a second disordered quantum dot, which couples to the partner Majorana modes that reside on the other side of this quantum wire. And if these wires are not too long, so that there is some communication, some crosstalk between their two ends, then precisely the right type of coupling will ensue. Similarly, with this topological insulator proposal, you could imagine having a thin film of a topological insulator with two black holes created on two sides, and there's a weak overlap of the wave functions through the bulk of the insulator. That's how they get coupled. If you squint your eyes, this is a graphene flake, but it's a bilayer. So again, each of them creates a wormhole, a black hole in a way that I discussed. And if you put two in close proximity, you basically get two such coupled systems. Now, the key challenge in all these proposals is that the two SYK models have to be identical, not just statistically, but microscopically. So these couplings, J, have to be exactly the same for this to work. Basically, if you make an excitation in your left SYK model, it gets scrambled due to quantum chaotic nature of the system, and the other one has to unscramble it. And if the J's are not just right, then that doesn't work. And of course, it's basically impossible to create two quantum dots, for instance, that are microscopically identical. So that's the key challenge in these proposals. The only way this is going to work is when there is some symmetry that relates the two sides, which is not quite really the case in any of these situations. But we're thinking about ways how this can be circumvented, but I'm not ready really to talk about that. This is just to show that there's ideas to go beyond a single SYK, and this is some of them. So in the last 5 or 7 minutes that I hopefully have, I'd like to answer the second question. Suppose we had these systems in the lab. Can we do something interesting with them? And I think the answer is yes. And here's one example. What I'm going to propose is that these systems would be good in diagnosing quantum chaos in systems where you cannot really force backward time evolution. And let me remind you about quantum chaotic behavior. In quantum systems, chaos is characterized by the idea of the operator growth. Basically, you look at this quantity, a commutator squared between two initially commuting Hermitian operators. One of them is evolved forward in time. And in chaotic systems at intermediate times, this quantity experiences exponential growth, which signifies chaos, just like exponential divergence of trajectories in classical chaos. A little bit of math, sorry about that. So if you expand that commutator, you get 4 different terms. The first line are the so-called naturally time-ordered correlators. These are correlators that correspond to reasonable quantities that can be measured in ordinary causal measurement. You perturb the system, you measure something, and they correspond to these naturally time-ordered correlators. But the second line, and this is actually where the chaotic behavior is manifested, are the so-called out-of-time order correlators, and these do not correspond to sensible measurements. And yeah, I don't have really time to go through this in detail, but basically if you look at the structure of these correlators, the ordering of time argument 0t, 0t, you find that to interpret this, you basically have to sometime during the measurement run your system backward in time. So it's this part of the inner product here. You start from the ground state, you wait time t, evolve system forward, apply operator w, but then you have to apply operator at time 0, meaning you have to evolve back in time. And this is a generic feature of these out-of-time order correlators that you have to really evolve system backward in time to measure them. And how do we do that? Well, in some systems where we have lots of control over all the microscopic degrees of freedom, one can reverse the sign of the Hamiltonian, and then forward time evolution with this minus h looks like backward time evolution, which is written down here. But in most systems, especially in solid state systems, this cannot be done, right? Hamiltonian of a solid is what it is. You cannot reverse its sign. So these OTOC and quantum chaos actually have been measured in systems where you can do precisely this. When you can reverse the sign of the Hamiltonian at will, then you can do this. So for instance, this is a trapped ion quantum magnet, and the algorithm involves evolving system forward in time and then backward in time, and this gives you this out-of-time order correlator that quantifies chaos. Another system here, this is a magnetic resonance quantum simulator with a certain type of a molecule. And again, you have evolution forward in time and then backward in time, and you can extract this exponential growth of this chaos correlator. But again, in naturally occurring many-body systems, you cannot do this. The electrons just behave according to whatever interactions are there, and you cannot run time backwards. So is there an alternative? And the claim is that yes, if you can put a system into this thermal field double state, you can measure these out-of-time order correlators by ordinary causal measurements on the combined system. So mathematical result, which is actually quite easy to derive, is this. And I, again, don't want to go into that, what exactly it means. I will explain that in pictures. Basically, what this says is that if you have a pair of identical systems that exist in this entangled thermal field double state, and you perform an ordinary causal measurement that involves both sides of this combined system, the result is equivalent to measure out-of-time order correlator in one of those systems at some temperature, inverse temperature beta, that corresponds to the temperature of this thermal field double state. So, this is a possible application of a wormhole. It gives new family of protocols that can allow you to probe out-of-time order correlators in systems where you cannot really affect backward time evolution. And the protocol looks something like this. You construct a pair of identical systems, prepare them in the TFD state, and then perform an ordinary causal measurement. In pictures, it looks like this. The challenge of backward time evolution has been replaced by the challenge to prepare this TFD entangled state. But as we've heard, this can be prepared efficiently by coupling two identical subsystems in a specific way and then cooling them down to the ground state. This has been shown by these authors that this is generally possible for a pair of chaotic systems. We've seen an example on a pair of SYK models. Basically, you just add this interaction between the two sides through some operators that are identical on the two sides. And then the ground state is close to thermal field double, and you can then perform this type of measurement. So what would you measure? And here's another interesting result. At first, we thought you would have to do some sort of non-equilibrium type measurement to excite the system, wait, and then measure something. It turns out it's sufficient to measure a two-sided causal correlator with V left and V right being just two arbitrary operators that act on left and right side respectively. And you do that measurement in the ground state. It turns out that if you expand this in short times, this ordinary left-right correlator contains an OTOC, out-of-time order correlator contribution in this expansion, and therefore one could actually extract this chaos exponent from just looking at ordinary retarded correlator between the two systems. I reviewed some efforts how to construct black holes and potentially wormhole analogs in a laboratory. In principle, it's doable. These are difficult experiments, and hopefully we will hear more from experimentalists what they think about this. The wormhole type setup where you couple two such chaotic systems could be good for something. For instance, one can use it to diagnose quantum chaos without having to perform backward time evolution. Thank you very much for your attention.